Now we're in a new section. We're going to be taking a look at differentiation, and we're going to start with the derivative as a rate of change. Now the derivative of a function describes how fast and in what capacity a function is changing at any instant. So rates of change. Now if you look at this graph here, y equals 4x minus 10, the graph at every point is changing at a rate of 4, right? Because I can just look at that and be like, hey, yeah, my slope, that's going to be 4. Now for the purposes of notation, if we say that the equation y equals 4x minus 10 represents the equation of the line, then y prime equals 4 is the derivative equation. Note, this little symbol here means that it is the equation representing the derivative. Now, there are various notations that represent the derivative. We can say y prime, sometimes we have f of x, right, or f prime x, dy over dx, this is the change in y over the change in x, or dx. All of these different notations represent the derivative. Now the definition of derivative here is the limit as h goes to 0 of f of x plus h minus f of x all over h. Now you should be looking at that and being like, wow, that looks like the difference quotient. And guess what? It is. You have actually essentially been doing the derivative all along every time you've been doing the difference quotient. Now why is there a significance to this idea of as h goes to 0? Well, let's look at this graph here. If I were to, let's say, pick this point here, that's x, and so then therefore that's f of x. Well, if I were to pick some other arbitrary point on that graph and I were to connect the two, we call that the secant line. And you can find the slope between that, and we call that the average rate of change, right? So for in this instance, this right here, we'll say that the distance here is some arbitrary distance h, and if we were to calculate this, we're going to then say, this would be our average rate of change. Now, the problem here is as I move this point closer and closer and closer and closer and closer and closer and closer, what's actually happening is my value of h is clearly shrinking, right? The value of h is getting smaller and smaller and smaller as I move along this. So it moves closer and moves closer and moves closer. And if I say I pick the same point, right, it doesn't matter, x1, y1, and x1, y1, right? It's the same point. If I go through and I do the slope formula for this, I get 0 over 0. Well, 0 over 0 is undefined, but remember, when it comes to limits, 0 over 0 has meaning. And so the idea is, instead of just saying it's the same point, well, I'm going to say it's going to be some distance h away, but I'm going to say h is 0, which is why I now have the limit as h goes to 0. So essentially, algebraically, it looks different because I have this h that's being added as a distance, but essentially that h is just 0. And so that is how we're able to kind of manipulate the situation a little bit so that I can find what the instantaneous rate of change is. And so essentially, we're just saying that that h distance is going to be 0. Now, you're going to see this phrasing, slope of the tangent line. Now, what does that mean? Along this graph here, on any point, let's say if I pick this point here, essentially, the slope of the tangent line is going to be the slope or the line that's created that's perpendicular to that point. And so as this point moves, so does the slope. And so every point, that instantaneous rate of change is going to be different. Now, I think a good visualization of kind of thinking about it is if a caterpillar was kind of like walking along this, and you imagine this caterpillar moving around, how the caterpillar is lying on top of this is essentially that tangent line, or the the slope that represents the tangent line. And so depending on the point that's being picked, we know that the slope is constantly changing here. That's bad drawing. That's better. But essentially, as you go through, the slope is going to constantly change, and you have all these different tangent lines that represent it. Now, that's essentially the slope of the tangent line. In this example here, it says use the difference quotient to verify that the derivative equals 4 if that's my equation. So we need to use the difference quotient. So f of x plus h minus f of x all over h. And so I get 4 times x plus h minus 10 minus my f of x all over h. Well, this is going to give me 4x plus 4h. The 4x minus 10, positive 10. And so you're going to be left with 4h over h. The h's cancel out, and so that we get 4. And so I could say that my dy over dx equals 4. So we have verified it. This one says that use the difference quotient to verify that if the derivative with at x being 0, right, that's your x value, the slope is going to be 0. So for this instance here, we need to do the difference quotient again. So f of x plus h minus f of x all over h. And so here you're going to get 2 times x squared plus 2xh plus h squared plus 2 minus 2x squared plus or minus 2. That's all over h. Distributing the 2 through, you get 2x squared plus 4xh plus 2h squared plus 2 minus 2x squared minus 2. The 2x squareds cancel out, the 2's cancel out, so you get 4xh plus 2h squared over h, and h from each of the terms cancel out, and so you get 4x plus 2h. So now we said it's the limit as h goes to 0. So now I have to plug in 0 for h. So I'm going to be left with 4x. So that's the derivative, right? I can say that y prime equals 4x, but now it's saying the value when my x is 0. So now I need to plug in 0 for x. So what's going to happen is I get 4 times 0, and so that gives me 0. And so I have just shown that y prime of 0 equals 0. Now, when does a derivative not exist? Now, the graph of the function has a cusp at x equals c. And so that's going to be this picture right here. Notice it has this sharp turn, or we call that a cusp. The function is discontinuous. So you see how at this value c, there's like this jump. And then the tangent line at the function x equals c is vertical. So as it moves through, there's like this instantaneous blip here in which the tangent line is going to be vertical, and so therefore you can't have a derivative because the slope would be undefined. And so at this value, the derivative wouldn't exist. So these are the 3 cases in which a derivative does not exist. Now I'm just going to set up these given problems here. You're going to see other types of difference quotient examples, meaning how would I take the derivative of a square root or of a rational, or what if it's both a square root and a rational. Now I'm not going to go through from beginning to end to solve it, but what I will do is kind of set up and show you what the secret is. And you can always go back into your pre-calc videos and watch the difference quotient to be able to go through and do everything. So remember the difference quotient, the limit as h goes to 0 of f of x plus h minus f of x all over h. Now whenever you have square roots, the trick here is you have to multiply top and bottom, so the denominator and the numerator, by the conjugate. Then, once you have that, because this is being multiplied like that, you would go through and you distribute this times this, this times this, this times this, this times this. And when you go through and distribute that, you're going to find a way to cancel out this h, because we got to get rid of that h there. Because we plug in 0 for h, we get 0 over 0 or undefined. We got to get rid of that h. And so that's the trick for this. When we have rationals, once again, the limit as h goes to 0, we get 1 over x plus h plus 2, so f of x plus h minus f of x all over h. Now the trick here is you multiply both the numerator and the denominator by what the common denominator is. So the common denominator is both of these together. So it's both of those. So you're going to multiply every single term by that. You're going to multiply the bottom by x plus h plus 2 times x plus 2. This by x plus h plus 2 times x plus 2. And this x plus h plus 2, x plus 2. So you multiply every term by that. You're going to see things cancel out, and then with what's left over, it's going to cancel out with that h. The last one, this one is work intensive, and you're going to combine both ideas together. If I plug in the x plus h minus f of x all over h, you're going to do both. The first thing you're going to do is pretend like it's rational. And you would multiply by what the common denominator is. So x plus h plus 1 times x plus 1, x plus h plus 1 times x plus 1, square root of x plus h plus 1 times square root of x plus 1. Those cancel out. Those cancel out. Now when we rewrite this, I have the square root of x plus 1 minus the square root of x plus h plus 1 all over h square root of x plus h plus 1 times the square root of x plus 1. Now if you notice, there's a square root in the numerator. And so then the second thing that you're going to do is now treat it like it's a radical equation, which means you're going to have to multiply by the conjugate. X plus 1 plus square root of x plus h plus 1 Now note, you don't have to worry about distributing all that through, just leave it alone for now. But after you do multiply the top through, and you go through and you multiply everything, etc., you're going to find out that then you're going to see an opportunity for the h's to cancel out. And remember, it is the limit as h goes to 0, so once that h cancels out, you'll then plug in 0 for h. So what is the derivative? The derivative represents the instantaneous rate of change at a given value. And we can express that as an equation. Now the difference quotient is the derivative as h approaches 0. So the difference quotient, what we talked about in pre-calculus, does represent the equation of a derivative when we add the concept of a limit to it. Now remember, it is not a derivative if there is a cusp. It is not a derivative if there is no derivative if it's discontinuous, and there's no derivative if at the value, okay, it gives you this vertical slope. So just a few things to remember, and it's only at the value x equals c. So at that value c, if there's a cusp, if it's discontinuous, and it creates like a vertical line, or the slope is vertical, there is no derivative there. Now, we kind of went through the difference quotient. With the polynomial, you're going to use factoring to kind of reduce it. With radical, we're going to have to use the conjugate. For rational, we're going to use the common denominator, and when they're both together, you're going to use both concepts together. You're first going to find the common denominator, and then you're going to use a radical to simplify. This does conclude our lesson. If you have any other questions, please leave them in the comments.